Number 63 from the 1998 ACS exam. Ask us which monomer will readily undergo anionic polymerization. So before we even look at the molecules, let's just think about what possibly would anionic polymerization mean. So polymerization means, right, we did a polymerization, so it's going to be a bunch of molecules coming together, right, a bunch of monomers. So it would be mostly a big molecule. What does anionic mean? Anion means what? Negative charge, right? Anion means negative charge. So if you look at the molecules, that's A, that's styrene. Alpha beta unsaturated ester, just an alkene, then an alkene with an OCH3. So at this point, this is really tough. Without going into too much detail about what an anionic polymerization is, one way you can think about, it's really, without giving you a lesson on anionic polymerizations, I can explain this answer to you. So the answer is B.
Did you eliminate any of these?
So let's think about why we could eliminate some, right? So if I looked at these, I would say C and D look really similar and really simple. And a lot of these things that we've been doing have been a lot more, the more resonance in some way, shape, or form going on makes a difference. So at least I think you could eliminate C, just be like, well, that doesn't have as much resonance or sharing of electron capability as everybody else. Right? If you just think about, if you looked at these, what do they all have in common? They all have a pi bond. But this one doesn't have anything else, really. Like this has lone pairs, this has another pi bond, this is a benzene ring. So at least I could eliminate one. Right? The other thing to think about is, so it's anionic. Which one of these could stabilize a negative charge best? And so which one of these have you seen with a negative charge? B, right? See, B you have, right? If it's the reason you've seen B with a negative charge, though, and it kind of, if you had a nucleophile, we've talked about alpha beta unsaturated systems, right? They're electrophilic where? At the beta carbon, or not the alpha, or the carbon of the carbonyl. Now, in a polymerization, something has to light the match. Right? So let's say the initial nucleophile attacks there. What did we form as our product? We formed a nucleophile, right? We formed an enolate. That's an anion. So really, this nucleophile really might as well be the initiator, like we talked about right before. So it starts it, right? And because it's an alpha beta unsaturated carbonyl system, you form an enolate. Versus here, right, you wouldn't form an enolate, and you wouldn't form an enolate here. But this is do your best guess. If you've never seen anything like this, don't pick it. If you've never seen me draw anything like this, don't pick it. Right, you've seen me draw these three things, and this one looks at least complicated. You got a 50-50 shot. But this is the reason why. There's a reason why. It's not just, but that's the reason why. For cationic polymerizations, this is actually more likely. So one way to think about this, for cationic polymerizations, the thing that starts it has to be the opposite of what it is. Or it is what it is, sorry. So cationic, this would attack an electrophile. And there'd be a plus charge here, and then this would be the next one. But this is anionic, means the monomers become negative. Here the monomer would become positive for cationic. Number 27, you have a ketone, acetone, and you have methylamine, and you have NaBH3CN, or they're saying H2 in a catalyst, which would basically mean palladium. So the tricky part here is you're used to seeing an amine and a ketone, and you should immediately think what? So what kind? You should say, what kind of amine is this? It's a primary amine, right? And usually you need acid. So I take a couple issues with this problem. This is a bad problem for a number of reasons. Well, maybe it's not. Maybe it is. Maybe it's not. So, well, no, it is. So really, they should be saying this. Really, they should say primary amine ketone, and then step 2 should be this. This should be step 2, and these two guys together should be step 1. So a primary amine and a ketone, if they're going to react, normally we like to have an acid catalyst to make this go a little faster. But what are they going to turn into? An imine. Right. That's what they would turn into, right? Everybody's on board with that. In the second step, if you treated that with H2, palladium on carbon, or this reducing agent, what is that going to turn into, do you think? It's basically treated like a pi bond. You're going to reduce it. You're going to add H and H, and you're going to end up with an amine and 2 new hydrogens on it. And that would be product A. So the tricky part here, if you look at the answers, so A is the right answer. B is probably the next best one. But if you see B, you should ask yourself, well, what the heck was the NaBH3CN and H2 for? Right? They wouldn't put a reagent on there unless they wanted you to use it. Right? So you should know right away, well, it can't be B. Because they had those two things add hydrogens. You should see H2 and say that adds hydrogen. And when I make an imine, this isn't adding hydrogen. Right? So if you're looking at the answers again, C seems silly because how are you going to make an amide from a ketone? And they're showing you there's no way. You don't know a way to make an amide from a ketone. There's no way to turn a ketone into an amide. Haven't shown you that. And the other one would be an intermediate on the way to the imine. So really, it's between this and this, the two answers. And if you look and say, wait a second, how to use this? I haven't used this yet. What was the point of this reagent? Every reagent must be used. Pick A. Number 14 is a good one, having to do with acid strength and remembering inductive effects. So it's 1, 2, 3. We draw the 4 carboxylic acids out here. So in the first one, we have a chlorine on carbon there. On B, there's a chlorine and a fluorine. Here, there's a fluorine and a fluorine. And here, there's just a bromine. So taking a step back and look at this, right? What does acidity refer to? Right, these are all carboxylic acids, so that means we're looking at the strength or the reactivity of this OH bond, right? And we look at what's different between all of these. Right, so the easiest thing to look at, well, I have chlorine, fluorines, and bromines. Fluorine's the most electronegative, then chlorine, then bromine. I would guess the closer this is, the more it would affect the polarity of this bond, right? And don't forget, right, if I drew this, these bonds are Sp3, right, hybridized. So they are pulling, right, in an uneven way. It's not like an even pull. It is an uneven pull because they're Sp3 hybridized, right? So for sure, the fluorine is the most electronegative. 2 fluorines would be better than 1 bromine, or a chlorine and a fluorine, right? Chlorine is still farther away. So this answer for sure is C. But remember, like there's gonna be questions about what's the best acid, what's the worst acid, best base, and be thinking about resonance, right? If you form a more stable product, right, because of resonance, that makes you more reactive. The starting materials are more reactive because you have a more stable product. Think about, electron withdrawing groups, where they're at. That's going to play a role too. Good.
Rate these now as well?
Hmm?
Like 1, 2, 3.
Yeah, I can rate these. So I would rate these I would probably say C is for sure 1. So if we said A, B, D, so C is the most acidic. What do you guys think the next acidic is? B, good. And the next? D. Like look where, like, yep, B is closer than, right? So I mean that's a tough one. Whether, I mean, between B and A, I don't know. Right, because between D and A, because chlorine is more electronegative, but it's farther away. Bromine's less electronegative, but it's closer. I don't know. I do know that C is the most acidic though. It has the lowest pKa then. Don't forget that too. Low pKa. Acidic, low pKa, just like low pH. Number 15 is another acidity question, and this one doesn't have to do with electronegativity, it has to do with hybridization. They're trying to see if you remember hybridization states in molecular orbitals. Basically, they're asking you, let's see. And they're saying, was it this one? Or they're saying this one? They're circling these 4, and they're saying which one's the most acidic. So this is A, this is B, this is C, and this is D. Classic question. What's the difference between these? What the hybridization say the carbon they are bonded to, right? Right? So A is bonded to a what kind of hybrid? What kind of hybridized carbon? Yeah. Sp2. What about B? What kind of hybridized carbon is B bonded to? C. Sp2 and D. Sp. Which one of these would form the most stable product? Which one's going to be most likely to stabilize a negative charge? It's D, right? Because D has it, right, an sp orbital, remember, which was fat. So if you put a negative charge in there, that's close to the nucleus, which is plus charged. Sp2, right, a little bit longer. Sp3, longer yet. Also, another way to eliminate answers here, if you see the differences between them, right, if you knew, okay, well, A is sp2, B is sp3, C is sp2, D is sp. The answer can't be A or C. It can't be A or C because both of them are basically the same type of hydrogens, right? They're not benzylic, right? So don't be careful, right? Because if there's something special about the benzylic position, but right, if all else fails, eliminate the two that are the same. Can't Then you got a 50-50 shot between sp3 and sp, and hopefully you remember, right? Just by thinking, right? Wait, like ethanol has lots of things have sp3 CHs. They can't be acidic because that'd be really weird, right? Which one looks the funkier, the weirder one? Pick that one, right? Just as a reminder, right? This deprotonating a terminal alkyne was the only way we knew how to make carbon-carbon bonds the whole first semester. So we hit this pretty darn hard, right? Terminal alkyne, that sp terminal alkyne. SPCH. Also remember, that's around, right? This is a good chance for me I'm going to segue into an IR explanation of what things people need to know for the exam as far as IR and NMR. So I'm going to call this my IR tutorial. I'm going to leave that there because that's nice to have those CHs. What do you need to remember? For IR, remember regions. IR, remember regions. OH, NH, and the OH from a carboxylic acid are all where? They're all what kind of peaks? They're broad kind of peaks, and they're strong, and they're like 35 to 3,000, right? There are more specifics for each one, but that's that broad OH, NH, carboxylic acid, OH region. the heteroatom OH-NH region. So you should know that, right, and what they look like. Another region is the CH region, right? So these guys gotta have their own thing. The CH region is split up between SP, Sp2, and Sp3. The most important thing to remember there is Sp3 CHs are below 3,000 always. So if there are no CHs or peaks around 3,000 or above 3,000, right? You don't have any Sp2 or Sp CHs, right? Sp2 and Sp are above 3,000. Right, so if you don't have anything above 3,000 in that little CH region, right, and this is around, 3,300, that's bad, 3,300 to 2,900. If nothing's above 3,000, you have no Sp2 or Sp CHs, which is important to know because if you had could you have a benzene ring with CHs if nothing was above 3,000? No, right? So you can eliminate answers this way, really fast and easy, right? Anything below 3,000, that could be an Sp3CH. Anything above has to be Sp2 or Sp. So if they're not there, you don't have them. Another region. Let's call this one the triple bond region. Nitriles and alkynes, right around 2,200, right? Little peaks around 2,200. They're usually pretty weak, right? But now if you had a terminal alkyne, right? So here's a classic problem they'll do. They'll say there's a peak at 2,200, and they'll say there's no CHs above 3,000. Can it be a terminal alkyne? Could it be this alkyne right here? No, it has to be a nitrile then. I think there was a problem like that I worked on the 8 a.m. class with, right? So, right, process of elimination, right? Think about what has to be there. If I have a terminal alkyne, I have to have both that CH and the triple bond. I can't just have one or the other, right? So that's the triple bond region. And then, of course, there's the C double bond O region, and that's around 1850 to 1650. Yeah, I think I highlighted this on problem 65. I did in the 8 a.m. class from Friday. It's the last problem I did. Take a look at that. It's the last problem I did on the 8 a.m. class. I walked through that. Right? So C double bond O is 1850 to 1650. Again, you can try to memorize these. I don't think it's absolutely necessary. Most of the problems you can figure it out without having that exact knowledge, right? Without having that exact knowledge, for sure. And they're usually pretty strong. Yep, they're usually pretty strong peaks. Good. So what about NMR regions then? What do I need to know for the exam? What do I need to know for this? NMR regions, we got to remember a couple of things about NMR. First, what does NMR tell us? It tells us the number of different H's is equal to the number of peaks, right? Number of different H's equals number of different peaks. The area under the peaks represents the relative number of H's of that type. That means a CH3 would be bigger than a CH2. The frequency where these peaks come out is affected by electronegative atoms. Deshielded, that means the electronegative atoms pull away the electrons. You become deshielded and you get pushed downfield. So if I'm next to an oxygen, I'm going to be farther downfield than if I wasn't. deshielded downfield. And then finally, there is splitting, that n+1 rule, the nearest neighbor rule. That indicates what other H's you are near. That's NMR. Now let's talk about the regions. So I'll close that, I'll put that over here. The 4 things about NMR. Now the regions, let's go from shielded, around 0, all the way to deshielded. So make that 0, I'm gonna make this 12. So from 0 to 1.5, these are just carbons that are not near anything that's electronegative. They're saturated. So they're very much shielded. We would call this even call it the saturated region. Saturated region. The next region over, between 1.5 to 2.5, we would call this the allylic region. So that means things like alpha CHs, things that are alpha to a carbonyl. And of course, obviously, allylic CHs as well. Right? Things that are not directly bonded to something that's electronegative, but maybe they're 1-2 bonds away. 1-2 bonds away. Right? They're 2 bonds away, so they're not fully filling it, but they're more than saturated. So those are allylic. All right, this is coming right from your thing you've been using all along. Okay. Next region, between 2.5 and 4.5. That's when you're on the same carbon that, say, is bonded to an oxygen. Or on the same carbon that's bonded to a nitrogen, right? Obviously, if you're bonded to an oxygen, you're going to be more deshielded than a nitrogen because an oxygen is more electronegative. And we call this, they call this the, you could also be bonded to a halogen. So if I said, instead of oxygen, if I replace that with a Z, so Z could be oxygen, nitrogen, or X, right? Chlorine, fluorine, bromine, or iodine. Maybe I'll make it. All right. The next step is the vanillic region. That's when you're actually directly bonded to that C double bond C. And that's from, 4.5 to 6.5. That's the vinyl region. Right? That's where you see the alkenes a lot. Be there. Hopefully when we all remember, aromatic region is between 8.5 and 6.5. That's the aromatic region. Right? And then anything beyond that, there's 2 kind of weird ones. Aldehydes and carboxylic acids. Both of these H's are kind of way out in between 9 and 12. They're out past there. So aldehydes, right, are pretty deshielded. So this is deshielding downfield. The more downfield you are, the more deshielded you are. The same holds true for carbon NMR. Right? If you're carbon bonded to oxygen, you're double bond to oxygen, you're going to be way downfield. Right?
Carboxylic acid would be more shielded than aldehyde, right?
I think actually a carboxylic acid is farther downfield than an aldehyde even. Yep, that's correct. So let's look at number 36. It wants to know how would you do this. right? So if I looked at this, I would probably say the last thing that had to go on was probably the ketone, but it's actually not the case here. This actually involves a reaction I didn't teach you. You know they're ortho to each other, so they're para to. So if we just analyze this tangentially, we know they're para to each other, right? Everybody can agree that these things are para to each other. So at one point, one of the things had to be an activator, right, or a halogen, right? Either had to be an activator or a halogen to get to go para. And we needed to add 3 carbons, right? So whatever we do, whatever the ones we look at, we need to have a way to add 3 carbons. So I would say three carbons. So at this point, it's pretty tough. Honestly, if you looked at this, I would say, okay, now let's go back and look. If I were you, I would go back and I would go look at the answers and see if there's anything. Do all of them add 3 carbons? So A adds 1 carbon, 3 carbons. Yep. B adds 1, and then it adds a diol, but I've never seen the diol. That looks really weird. Right, if I look at B, that looks like a lot of weird stuff going on, like a protection maybe, and then an attack. Yep. They all add 3 carbons, so that doesn't help. The key to this, quite honestly, is that you needed to know KMNO4 can turn a like toluene. The key to this is that KMNO4 will take, maybe I did show you this, maybe I can't remember. These 2 things reacting together will give you a carboxylic acid. I did show you that. Yay. Okay, good. KMNO4, benzylic CHs, right? Makes carboxylic acid. Okay, I did show you that. Good. That's the key to this. Essentially, this problem, going backwards, is going to be really hard. I would just start looking at the answers, or I would skip ahead to something else and work as best as you can going forward. All right, so this one you literally need to go through. I would argue you need to go through this step by step. The easiest way, actually, another strategy could be for this is this. You could say, okay, instead of having to go through from start to finish A through D, what you could do is go to the last reagent from each answer, and say, okay, the last reagent, what would this have been if the last thing I did was lithium aluminum hydride? Right? Could that have worked? Can I reduce? Could this have been a carboxylic acid? Could I have reduced this in the presence of a ketone? No, right? Could I, if I treated this molecule with lithium hydride, would a ketone stay there? No. Okay. So that's A. So that doesn't work. Let's cross that out. For B, the last thing they did was H3O plus. It looks like they had a Grignard and they had acetone. Acetone and H3O plus. So I don't know. Yeah, that could work. Oh, it's not acetone. It's a formaldehyde. Right? That's adding 1 carbon piece. So that could have been this. Right? Something could add to this if it was a Grignard and add 1 carbon there. So B's not bad. But say we're confused.
Yeah.
Right? The last thing, so for C, the last thing they do is this in H3O plus. That could maybe work. But it probably wouldn't work in the presence of a alcohol because this could attack there, right? Alcohols can attack acid chlorides. And then D, again, it's almost the same as B. So that's one way to do this. If you just looked at this and said D and B have the same last step, maybe they're probably the most similar. Let's investigate those two more. The answer for this one is B. And the best advice I would say is you go through and try to logically do each step. If they're giving you the answers like this, I would go through forward synthesis ways and see if I could actually do each problem, right? Go through every single one and draw the products for that and see if it gets to the right product. Versus trying to look at this in a retrosynthetic way, I wouldn't do that. I would just look at A, do all those reactions, see what I get. Do B, do all those reactions, see what I get. C and D, do all those reactions, see what I end up with, right? Worst case scenario at the end, this is when last, this problem's a lot of work. I would skip this problem and go to the next one. This problem's a lot of work. There might be super easy questions that are at the very end. Always remember that. These questions are not in order of difficulty by any means or topic. If you see a hard question like this, go ahead and skip it. Go to something else. So let's look at number 39, and we'll look at it in terms, and we'll expand upon this problem, talking about activators and deactivators and which ones are which and where they direct. So for this one, the question asks, what is the order of reactivity of these substituted benzenes towards electrophilic aromatic substitution? In electrophilic aromatic substitution, the benzene ring is what? The nucleophile or the electrophile? Benzene ring is the nucleophile. So the more electrons you push towards the benzene ring, the more reactive it would be, right? So you want electrons towards the benzene ring, right? So if you remember, right, before I even look at the things, what is electrophilic aromatic substitution? The ring is the nuke. Push electrons towards it. Better nuke, right? Basics, right? That's what they're asking here. Before you even look at the molecules, that's what they're asking. Do you know what electrophilic aromatic substitution is and what it means? Benzene ring is a nucleophile. If you have groups on there that push electrons towards it, they'll make it more reactive. What kind of groups push electrons towards it? Hyperconjugation or lone pairs, right? And some groups don't want to give their lone pairs as much. So they're called the halogens, right? Is a chlorine going to want to be giving up its lone pairs that much? No, but it's still going to a little bit, but not like oxygen or nitrogen would, right? So in this case, the molecules they have for us are these. All right, so we want us to rank these. I think they say, they do the Roman numeral deal to you. Which of these is going to be the most reactive, the best which one's going to be the best nucleophile, which one's going to be the worst nucleophile? So let's think about which group. So the worst nucleophile is going to have the group that's the most electron withdrawing, taking electrons from the ring, right? Because we just said, push electrons towards it, make it a better nuke. Which one's going to make it which one's going to be the worst nuke? Two. Why?
Because the NO2 group would drop.
Because it has the NO2 group, the biggest electron withdrawing group, right? NO2, remember, you can draw, hopefully for the love of God, you can draw the Lewis dot structure of this for me. So I can sleep at night, right? You can draw that for me. Yep, good times. I only ask you to like two Lewis dot structures. SO, I can't even say it. H2SO4 and NO2. That's pretty much it. That's all I ask. Joan was asking you to do some god awful things with half the periodic table last year, and I'm just asking for two things. Huh? HNO3, yeah, HNO3. Okay, so I had three. HNO3, H2SO4, NO2. So, but that's a super electron withdrawing, right? Because, right, Why do we need to know the Lewis dot structure? Because we can see that there's a plus charge in that nitrogen. So we know that that's not just a nitrogen that has a lone pair, right? Because this nitrogen right here has a lone pair. So can that nitrogen donate electrons? Yes. Does this nitrogen have a lone pair? No. Right? So that's why we need to know those Lewis dot structures. Because every nitrogen is not the same. This one has 4 bonds already. So it's not donating electrons. This one can. So 2 is the worst. So 2 is the least reactive. I'll put that at the end. Which one's the most reactive?
Well, would you look at it? There's only one answer with 2.
There's only 2 with 2 electron donating groups, right? Right? So 3 would have to be the best. And then 1 is in the middle, right? So 1 has an electron donating group and an electron donate hyperconjugation here. And this has a lone pair, but this has lone pair resonance the other way too. Whereas this has lone pairs and lone pairs, both can go in, right? There's no, and of course hyperconjugation is not as good as lone pair resonance, right? Not as good as lone pair resonance, right? So if we want to take this, expand this out to activators and deactivators, right? To remember what these are. So activators obviously donate electrons in. So some activators, the classic ones are, nitrogen with what doesn't matter what it's bonded to, R2 has a lone pair, oxygen with an H, right? If this was the benzene ring, ethers, right? Anything with a lone pair next to the benzene ring is going to be an activator, except the halogens, right? Except the halogens. And some activators are better than others, right? If I have this ester is an activator. But is this ester as good as an activator as this ether? No, because this ester has resonance going another way too. Yes. Right? So where do activators direct? So activators make the ring nucleophilic, and they direct ortho and para. So they put whatever electrophile you're adding either in the ortho position or the para position. All right? And whatever one's the best activator does it. And activators are more important than deactivators.
There are more activators than there are.
Well, no, that just saying that if you're doing a reaction and you're trying to decide, okay, I have an activator and a deactivator on the ring. Right? So like this one right here, you have an activator and a deactivator. Which one matters to deciding where things should go? The activator matters where it should go. So the activator is dominant over the deactivators always.
Methyls are activators?
Methyls are activators because of hyperconjugation, right? So the only confusing ones, right? So nitro's a classic deactivator, right? Other deactivators. So obviously NO2. Ketones can be deactivators, right? Because that carbon of the carbonyl is delta plus, right? Amides can be deactivators. Don't get confused, right? See what they did here? When the nitrogen of the amides bond to the ring, that can be an activator, versus when the nitrogen's on the other side of the ring, that's a deactivator now. Right? So make sure you remember if you're bonded to the carbon of the carbonyl, that's delta plus. If you're bonded to the oxygen or the nitrogen, right, that can be an actual electron, that can be an activator. Those always, deactivators always direct where? Meta. And then finally, the confusing ones that are deactivators that direct ortho-para are the halogens. So I would just give them their own deal. So halogens, and that's fluorine, bromine, chlorine, and iodine. Right? They all have lone pairs that can donate electrons, but they're still pulling away electrons inductively, so they're still considered deactivators. But because they donate lone pairs, they direct ortho and para. So halogens are in their own class. So one of the harder questions actually that appeared on the exam 4 from 2014 was something called, basically did a Michael edition, and it's called, actually the whole thing is called the Robinson Annulation. It's where you take two ketones or aldehydes, one of them has to be an alpha beta unsaturated, and one of them is not, and you form a ring, and you also lose water. So, yep, I'll show you. So there's a couple things to take away from this besides taking away the whole thing. If you can't take away the whole thing, there's a couple things to take away. So one of the terms is a Michael addition. Not named after me, sadly. Right? It's the same as a conjugate addition, which basically means the nuke attacks where? The beta position. Right? So there's three ways to say the same thing. Perfect. Conjugate addition, Michael addition, attack the beta carbon. So Michael addition means you attack the beta carbon. Right? And if they tell you to do that, you just do that. You don't worry about the nucleophiles. So in this case, they're showing us this as a final product. Now, one of the things we didn't talk a lot about was training our eyes to do this. Right? How to see which bonds are which. Right? That's tough to do. Right? That takes some time and work. But we can do it now and take a look. So what you need to see here was, so you know when you see a Robinson annulation, you know at least one of the pieces had to be something like this. And we don't know what's here, and we don't know what's here or here. But we know it had to be an alpha beta unsaturated system, ketone or aldehyde. In this case, it has to be a ketone. And I know that because, well, I see it. There has to be a ketone. So what you need to see here is that Robinson annulation is also a condensation, meaning that you lost water, right? So this pi bond is where you lost, right? If we did an elimination, a condensation, this pi bond must be where we lost that water. So if I took one step back from here, where would the OH be? I'm going to start numbering these carbons. I'm going to say 1, 2, 3, 4, 5, 6. Where would the OH have been? Which carbon would have had the OH? Had to be carbon 6. Right? Had to be carbon 6. Now, why did you say 6? Those of you that said 6. Because you could, right? Because the carbon 1 is the alpha carbon of that ketone. Those hydrogens are acidic. You can do the elimination that way, that E2 elimination. So let's draw that out. And 1, 2, 3, 4, 5, 6. Now, if you had to guess one more step back, what bond was the next bond made? Well, previous bond made here. Which bond do you think is going to be the most polar bond? 1 and 6, right? What if I broke 1 and 6? So here I broke the pi bond, but what if I break 1 and 6? This is the pi bond. But if I broke 1 and 6, what does 6 turn into? So which part of if I broke 1 and 6, what's carbon 1, the nucleophile or the electrophile in that case? What's carbon 1 going to be? If you look at that right now, carbon 1 is what kind of carbon? It's an alpha carbon. So is that going to be a nucleophile or an electrophile? You deprotonate that and you make a nucleophile, right? You make an enolate there. Carbon 1 had to have been an enolate. All right, maybe if I draw it out. Because carbon 6, 1, 2, 3, 4, 5, 6. Maybe another better way to look at it? Look at carbon 6. What's carbon 6 bonded to? In this case, carbon 6 is bonded to what? It's bonded to an oxygen, right? If you're bonded to an oxygen, are you going to be delta plus or delta minus? Delta plus. So betting carbon 6 would probably have to be the electrophile. That means carbon 1 would have to be what? It'd have to be the nucleophile. So if you had a hard time seeing that carbon 1 is nucleophilic, take a look at carbon 6. Say, like, wait a second, carbon 6 is bonded to an oxygen. That's going to be delta plus. Right? That's going to be delta plus. Now, we're getting close. What's the next bond that we would need to break? Now remember, what's a Robinson annulation? What's our definition? You had to do a conjugate addition, a Michael addition, or attack the beta carbon. Which one of these is going to be, what other bond are we going to break now? 3 and nope. 4 and 5. Now, I'm going to be very honest with you guys. This is advanced. I'm not sure how pertinent or important. So individual ideas here are important. This whole package is pretty tough to see. Right? So if you can take away some certain things, right? If you see this kind of configuration, right? 1, 2, 3 carbons where there's a ketone, or you see this bond and there's an alcohol, right? You should be able to recognize that the carbon that's alpha, 2-carbonyl, is always going to be nucleophilic, right? If it has CHs, you can depronate. This will be nucleophilic. And if there's a new bond there and you see something bond to an oxygen, you should recognize that carbon as being electrophilic. You should be able to recognize that if there's a pi bond, and one of the carbons is the alpha carbon and the other one's not, that the OH must have been on the other thing because we did an elimination, right? Because that's acidic, right? So all these individual pieces you should be able to see. If I showed you this and said this came from a conjugate addition, this came from a conjugate addition, you should recognize that that means you had this and this. Right, because this carbon right here, 5, is not a conjugate, it's not a beta carbon to anything, right? It's not beta to this ketone. But carbon 4 certainly is alpha beta to this ketone. So you knew this bond had a break. So individually, each one of these steps you should be able to see, but the whole package, pretty tough. Does that make sense for each what we can take from each step? Taken individually, maybe what we can see, but as a whole, that's a lot to take in. So you should know, Michael addition means you attack the beta carbon. You should recognize an elimination product. The elimination, the OH, will always be beta to the ketone because the alpha CHs will be acidic and you can do an E2 elimination. If you're talking about this bond formed between an alpha and a beta carbon, the alpha carbon is always going to be nucleophilic. The beta one, especially if it's bonded to an oxygen, is the electrophile. If you have something like this, you know there's a beta addition, a Michael addition, a conjugate addition, all the same thing. You've got to find which carbon is conjugate, right? This ketone right here does have conjugate carbons, right? But they're not bonded to any other carbons, so they can't be the ones we're talking about. Each 3 pieces here has an important idea, but in total, knowing all these in conjunction with each other, very difficult, but you should be able to see each one individually for sure. So yeah, I'm gonna say that right now. So I take that back. I was wrong. There is another way you could do this. You could also say we could have broke 3 and 4. Right? You could have broke 3 and 4 and had a conjugate. Carbon 4 is conjugate to this ketone, so you could have broke 3 and 4 as well. So there's even 2 ways to do this one. Working on a Diels-Alder problem, which was highlighted in number 35. In the ACS test, but I'm going to take it another notch, show a sapling problem as well, how this all works. Biggest thing is going to be numbering carbons. So we have a diene part, the part that has 2 double bonds, and we have an alkene part, where there's only 1 double bond. They want to show us the product. So the most important thing to remember here is that Diels-Alder reactions, 1, 2, 3, 4, the butadiene. We need to get the double bonds right on the same side of each other. The alkenes on the same side. Now they're in a ring, they're already locked in conformation. So it makes it easier, so they have to stay there. And then we have 5 and 6. We're going to bring these 6 carbons together and form a ring. We're going to form 2 new sigma bonds, 2 sigmas, and 1 pi bond. The pi bond is going to end up between which 2 carbons? 3 and 2. So let me draw the arrows. So if you look at these arrows, what new bonds? So we have 2 new sigma bonds between which 2 carbons? Which carbons have sigma bonds? So I have a sigma bond between which 2 carbons? That's a pi bond. The sigma bond's already there. New sigma bond. 4 and 5. And 1 and 6. And the new pi bond is between 2 and 3. So the easiest thing I do right away when I see a Diels-Alder reaction is I just draw a 6-membered ring. And I number my carbons. 1, 2, 3, 4, 5, 6. Right, 1 and 6 had a new sigma bond, 4 and 5, and then there has to be a pi bond between 2 and 3, right? And from here, I just fill in the blanks of what else is bonded to those things. Because everything else in the molecule had nothing to do with the reaction. So 5 and 6 were also bonded to a 6-membered ring back here. Okay, draw that in. 2 and 3 were bonded to a 5-membered ring back there. Good, did that. 1 and 4 were bonded to 2 other carbons. So make sure those are still bonded there. Those are the tricky ones, right? That there's, now I'll erase that to draw it a little clearer. Now it won't let me, of course. Right, you see how there's 2 new bonds here? There's 2 carbons here. You can think of them like being wedged and coming up. But you could say those are 7 and 8. And these would be 7 and 8 here. So that's like a bridge. But the hard part about this is, the hard part is actually just filling in the other carbons after the fact, right? Find your butadiene, the 4-carbon piece, find your 2-carbon piece, make a 6-membered ring. 2 new sigma bonds, 1 new pi bond, right? It might have been the bridge, how you did the bridge up. That could be the part that got you, right? This is what it would be. The other part of the Diels-Alder, right? So things to recognize. 7 and 8 had to be on the same side because they're on the same side as in the starting materials, right? If I number these carbons 9 and 10, are 9 and 10 on the same side of the alkene? Are 9 and 10 cis to each other? So they need to be cis in the product then too, right? That makes sense? Right, that basically what I'm saying is that there's H's here, and both of these H's need to be either wedged or hatched, right, in the product. Right, if you're a cis alkene, you're going to be cis in the product. If you're trans, you're going to be trans in the product. That's the other big thing for the Diels-Alder. Looking at number 67 from the ACS 1998. Question asks us, which does not undergo SN2 readily? Right, so we should be thinking not SN2. So which things will not undergo SN2? Well, we know, the thing about hybridization states. What hybridization state does it have to be? Has to be Sp3, and it can't be very, right, and what kind of alkyl halides does it have to have usually? Can it be tertiary alkyl halides? So it has to be Sp3 and has to either be primary or tertiary. Secondary. Yep. Primary or secondary. But it has to be Sp3. Right? It has to be Sp3. Because we need to do that backside attack. So I haven't looked at the answers yet. But I see not SN2 and I should be thinking, well, this is what SN2 is, right? They're asking you, do you know what SN2 is? So if you immediately, before you even get influenced by the answers, you say to yourself, or write down in your note, an extra sheet of paper there, say, well, SN2 has to be Sp3 hybridized and primary or secondary. And now I'm going to look at the answers, and let's see what we have. And it wants the one that doesn't follow those rules. Not. Right? So the answers, the questions, A, and they don't draw these out for you easily, right? That's another little fun thing they do sometimes. They don't draw out the stick figure. They do CH2, CH3, so you got to draw it out. It helps to draw it out. So which one of these will not undergo an SN2? There's only one that's not bonded to an sp3 hybridized carbon. B, right? This is the answer. B is the answer. It's bonded to an sp2 hybridized carbon. You cannot do SN2 reactions on sp2 hybridized carbons. Let's say you had no idea what this question was asking, right? I don't remember what SN2 is, but you drew out these, and we're going to look at these. Which one of these, right? So what looks different, right? Things that look different or are different, right? So, okay, you say they all have bromines. Okay, that's all the same. You should ask yourself, what kind of carbons are the bromines bonded to? All right, hopefully you know hybridization at this point. Right? You should say, well, that's sp3, that's sp3, that's sp3, that's sp2. Well, that's different. And they're asking for the one that's not. It's got to be B. I could know nothing about this. If you gave me these four things, I bet I could guess which one would be the answer for whatever question you're asking. Right? Just raw logic. What looks different? What's not the same? Right? B. There is a reason, of course, but if you had no idea, right, that's how you could break this down. Say, wait, all bromines, that's not different. They're all, these three guys have carbons without pi bonds. I don't even know what hybridization is. These carbons look like the same. This carbon looks different. I guess it's that one. So number 69 is asking us, what is the predominant form of the amino acid serine at pH 1? So pH is 1. So they want to know the predominant form. And you don't need to know what serine is. They're not asking to know what serine is. But at pH 1, what do you know about pH 1? What does that mean? Acidic. And if something's acidic, what kind of charges are going to be around in acidic? Plus charges. What charges will not be around? Plus only. And this is like not just a little acidic. This pH 1 is like really acidic, right? So what charges should there not be at all?
Negative charges.
No negative charges. So I'm saying no negative. Now I look at the answers. Which there's only one that doesn't have a negative charge, and it has to be D. Now, how else could they ask this question? They could say, all right, at pH 12, what's the predominant form? That would be in basic conditions. And then what would you need? Right? All negative charges, no plus charges. They could say pH 7. And then if it's at pH 7, that's net neutral. So you'd have a 1 plus and 1 minus. So if you look at the answers, A would probably be pH 7. I'm guessing B is just garbage.
So if
C would be under basic conditions, under like pH 12.
So if they did say pH 12, how would you differentiate between B and C?
Look at C. C is a carboxylate. That's going to be deprotonated first, right? That's like carboxylic acid versus the O minus on the other one, right? You never would have a carboxylic acid not be deprotonated first, right? So I would say C is probably the pH around 9 or 10, right? If you get any higher than that, you need both of those H's gone. You'd have 2 minuses then. That's how I would. Yep. Good. All right, number 19. This one asks, which of these structures shown in Fischer projections represents a chiral molecule? So again, chiral molecule. The chiral molecule has asymmetric centers, which means it has to be an sp3 hybridized carbon with 4 different groups bonded to it. Right? That's the definition of chiral molecules, right? An asymmetric center. Chiral molecules have asymmetric centers. So we look at these, and we got to see no mirror planes, right? The other confusing thing, chiral molecules, don't confuse chiral molecules with meso compounds. Meso compound, right? Chiral molecules have asymmetric centers, no mirror planes. Whereas meso compounds also have asymmetric centers with mirror planes. So let's draw these out. CLH, CLH. That's good. That's A. B, Cl, Br. They're all, yep, that's good. C. And then D. So for both of these, they both require asymmetric centers. Right? So no matter what, they have to have 4 things bonded to the carbons, right? They have to have asymmetric centers. So which of these have asymmetric centers in the first place? Right? So chiral and meso refers to the molecule. Right? Molecules are chiral, molecules are meso. Asymmetric centers are like that carbon. Right? So which of these can we eliminate that actually does not even have asymmetric centers? Doesn't have an sp3 hybridized carbon, sp3 hybridized carbon with 4 different things bonded to it. Which one? B and C, right? Why? Well, methyl and methyl. Methyl and methyl, those aren't different. Heck, this is 3 methyls, methyl and methyl, right? These B and C do not have asymmetric centers. They don't have 4 different things bonded to sp3 hybridized carbons. So at the very least, if you knew that first part, you've at least eliminated down to 2 things, A and D. And now you look at A and you should say, well, look at A has an internal mirror plane, right? So that's a meso compound, therefore it's not chiral. So the answer is D. All right, let's just one last time. Let's talk about hybrid orbitals, hybridization states. Or just hybridization. And hybridization can be split up into 2 things. A hybrid state and the molecular orbitals for that state. Orbitals. Orbitals. Right? So the easiest one, everybody knows, is sp3 hybrid state. That, of course, is tetrahedral geometry, no pi bonds. The molecular orbitals for that, because all these bonds are equal, right? They're all the same kind of bonds. They're all 4 sigma bonds. The molecular orbitals have to be all exactly the same as well. So we mix 3 p's and 1 s, and we come up with 3 sp3 orbitals. 4 sp3 orbitals. If you take 3 p's and 1 s, that's 4 atomic orbitals. Mix them all together, you get 4 molecular orbitals out that all look the same. Right? I had to make all these bonds are the same. You can't tell me which bond is stronger. An s orbital is different shape than a p orbital, so it would have different orbital overlap. So we have to have all the orbitals be the same. Right? So they all look like that. And those are that's an sp3 orbital. So it's a modification of 3 parts p, 1 part s. Another hybrid state is sp2. Now all of a sudden, right, we have a pi bond. If we have a pi bond, we need to have a p orbital. So we don't mix one of our p orbitals. So we just bring that p orbital over. Right, that's a bad looking p orbital, but that's the p orbital. So what's left is an s and 2 p's. So we have to have sp2, sp2,
Why have we never said it like this?
sp2. So okay, so what does an sp2 orbital look like? So it's going to be a little more short and fat because it's 2 parts p, 1 part s. So that's what an sp2 orbital looks like. The last one would be an sp orbital. Now this one has 2 pi bonds. And this is associated with an alkyne. So if you have 2 pi bonds, you have to have 2 p orbitals to bring over. So a p and a p. Same looking p orbitals as before. So only thing left of the atomic orbitals is 1 s and 1 p. So those guys mix together and they form 2 sp orbitals. And now these guys, of course, are mostly, they're 50% S, 50% P, so they're pretty short and fat. And that's why when you put a negative charge in there, they're close to the nucleus, right? Terminal alkyne CHs, if this was an H here, that's more acidic because you form a more stable anion. Right? So that's why SPs are more stable because it's close to the nucleus.